In earlier times, we used to generate light only by converting electrical energy into a heated filament, and then it produces some light as well, like in incandescent bulbs. But this is not the most efficient technique, right? And therefore we moved to the atomic scale. We know electrons move in different energy levels. Let's consider two of them, E2 and E1. As soon as an electron moves from E2 down to E1, it releases a photon or light particle of frequency nu given by E2 minus E1 equal to h nu. This is called spontaneous emission, and the most famous device which uses this technology is LED or light emitting diode, which is nothing but a simple PN junction diode connected in forward bias. Let's understand. This is the band diagram. This is the P side, the N side, the conduction band and the valence band. When it's in forward bias, the electrons in the conduction band of the N side move and then they drop down into the valence band of the P side and recombine with the hole there. And when they drop down, whoop, the same spontaneous emission happens. What is the frequency of the emitted light? That depends on the material used. And by the way, this material of the semiconductor which makes this diode has to be a direct bandgap semiconductor. Just like you have the compound semiconductors when you combine the group 3 and the group 5 elements, gallium arsenide, gallium phosphide, etc. Silicon, germanium, these won't work. These are famous because silicon is abundantly found, it's resistant to temperature variations, but not for this application of light emission. Well, let's understand it by the way. What are direct and indirect bandgap semiconductors? Consider a semiconductor having an energy momentum diagram like this. This is the conduction band, this is the valence band, the lowermost point of the conduction band, the highest point of the valence band in terms of energy should have the same momentum for spontaneous emission to happen. If it is a diagram something like this, then it's an indirect bandgap semiconductor. I hope the concept is clear. So far so good, but this LED produces a light which is not very intense, it is not having a very high amount of energy. To produce an intense high energy light, we use something called stimulated emission. Let's understand that. Consider the levels E2 and E1. When a photon hits this electron at E2, you expect it to go to E3 because it gains some energy. But instead it goes down to E1. This also has a probability as per some equations of quantum mechanics. Not all materials support this kind of a process. There are materials, some compounds of yttrium and some other materials which support this process that when a photon hits the electron, rather than going up, it goes down. When it goes down, whoop, an emission of a photon equal to h nu. This is called stimulated emission. Now note that one photon hits, two photons go out. These two photons will again hit further electrons, 4, 8, 16, 32 photons will come out, and very soon we'll have a whole lot of photons. This is light amplification. So stimulated emission is always followed by light amplification. This device laser is called light amplification by stimulated emission of radiation. This material is called the active medium or the active layer or the lasing medium. Now there are certain conditions for this entire stimulated emission to happen. First of all, this active medium must be of a desired material. Secondly, there must be more electrons in the E2 level than in E1 level, a phenomenon known as population inversion. And thirdly, in order to have this population inversion, we need to provide some external energy to push the electrons from E1 to E2 artificially. If we do that, only then the incoming photons will be able to knock down these E2 electrons to E1. This external energy is called external pumping of energy. We can have optical pumping, electrical pumping. Energy can be given to these E1 electrons in different ways. And we must also have some sort of confined mirror-like structure so that the emitted photons keep reflecting and they keep amplifying within, and then you can make a small hole and all the light comes out of it. That is the focused laser. Now let's understand that one of the most common types of laser devices used today is called semiconductor laser or diode laser, which is nothing but again a PN junction diode connected in forward bias, but then you have an intrinsic layer or I layer in between the P and N. So when that electron hole recombination happens, it happens in this intrinsic layer. And we know that when the electron moves down from this higher to this lower layer, it will generate energy, and it is this energy which acts as the pumping energy for laser. And this entire eye layer is made of that active medium material, gallium arsenide or whichever material depending on the color of the light that you want. So that entire laser phenomenon will happen here, and the recombination of electron and hole will produce energy which will serve as pumping energy. And you make a hole here, you have the laser light coming out. And therefore you can understand that this laser technology is a quantum mechanical technology, because there is a probability of electron moving from E2 to E1. Furthermore, if you decrease the width of this eye or the active medium to a very tiny width, it will become something called the quantum well, where equations of quantum mechanics will be used. So this laser technology is a quantum mechanical technology. Apart from that, quantum mechanics is also used in tunnel diodes or Esaki diodes, which is nothing but a highly doped p-n junction diode connected in reverse bias, so that the depletion layer is extremely thin and electrons can move from the n region to the p region using the quantum mechanical tunneling effect. Lots of applications in oscillators, many others. So quantum mechanics is cool, and a comparison between laser and LED was done in this video. Stay in touch. Keep watching News and Statics. Share, like, subscribe, bye.